gosh, I don't want to say close.
Don't
to
mention
30
it.
years.
Yeah.
Less than 30 years. How about that? He got his diploma, which is essentially equivalent to a master's degree at the University of Basel. Daniel wasn't. He was already gone.
He was gone.
And then he went on and got his PhD at the ETH, the alumni, the Eigenosche Technische Hochschule, or the Swiss Federal Institute of Technology. And he had his degree in cooperation with University of Miami as well. A fellow who has an illustrious family named Daniel Bernoulli. Ever heard of Bernoulli? Bernoulli
No.
physics? No. Bernoulli? No? If you ever make a fire, you owe it to Bernoulli. And Gregor Eberle, who was also from the ETH and then went to the University of Miami. And he was still in Miami, isn't he? Great. After that, he went on and stayed there in Miami, a wise choice, and did a postdoc there. Then he came back to Europe. He had an expatriate syndrome of some sort, and took over the Limnogeology Lab, which was really sort of the transformation of deep sea drilling project, or ODP, into lake research. And the Limnogeology had a great history.
Your history.
Well, you know, I was just part of the team, and Flavio took that over and brought it to another level. After that, he was an assistant professor at the Schweizer Nationalfund, which is sort of the NSF equivalent in Switzerland, and he was moved on then to the head of the sedimentology group at ERWAG, and let me see if I can get this right, the Eigenosche Anstalt für Wasserversorgung, Abwasserreinigung und Gewässerschutz, which essentially is the Swiss Federal Institute of Aquatic Sciences and Technology. Doesn't translate at all. And then he's been in Bern since 2012. His research really works into, well, first of all, he has over 200 publications. And his work really works into sedimentary records as indicators of environmental change and climate change. Again, he's working in flood records, and I think you'll hear a little bit about something maybe related to that today. Sedimentary budgets of sources to sink systems, a lot of reservoirs in the system, so it's a really important question in Switzerland, and globally actually. Sediment archives of human environmental interactions. His work in the Patan with Mayan collapse has been, as well as in Patagonia, in Argentina. He works in petrophysical and geochemical sediment properties, which I'm sure we're going to hear a little bit about today, as well as sediment archives of marine and lacustrine subsurface, essentially looking at seismicity, sequence stratigraphy, and lakes as, I guess, paleoseismometry. Today we're going to hear about paleoseismicity and natural hazards, but first I want to just point out that Flavio, living in Bern, he's got one of the best lives ever.
I'm worried now. What comes?
If it opens up, then we're in heaven. Yes, indeed. Sorry, Flavio, you're victimized. So Flavio, what he's done in the city of Bern, which is one of the best cities certainly in Switzerland, and if not West Central Europe, he has this small, beautiful cabin up in the Emmentaler region of the Bernese Oberlands, and this is a cabin that's built in about 1750. It's just too beautiful, too pristine. And he's had to go through lots of hoops to make it a livable cabin because it was just owned by cows and other things before him. You can see it's a classic. It's beautiful. Upstairs living, sleeping, downstairs living, and no cows there, but they live down below. Flavio has a passion for beautiful furniture and interior design, and we have something in common. It's just
Look at how simple it is there.
Yeah, but see, there's the office, and then there's the house. Right? And so, this is a kochel oven, right? Which is the original way to heat the house. You put fire in there, and the ceramics pieces heat up, and they stay warm all night. and it is a great addition. And it took a lot of effort to get that thing up and running, that's for sure, right?
And you can sleep on top of it.
Yeah. The cat sleeps up on top of it. So just to give you a sense that this is really old, right? This is the door latch to the bedroom, okay? So forget the little knob that you got on your door.
But note that the lock is outside, so that's
And that's pretty interesting. Huh? So, in Switzerland, there's a lot to do with cheese and meats and bread and pickles, and this sort of captures it all, and is outdoor eating in the summertime, because weather can change pretty quickly up at the cabin. You can see the fog in the valley, and it's climbing its way up, and we were there, and within a matter of moments, this had happened. And so it can get cold in there, so having a cocktail oven is a good thing. And if it really gets wintry, that's what happens. So then you're stuck there for a while. But again, it's just my pleasure to introduce, let me see if I can get this out of here. Who's here? And Flavio, and again, it's a pleasure to have him. And he's talking about tsunamis in lakes.
Thanks a lot, David. Kind and unexpected introduction in this talk. It's really a pleasure to be here. Thanks a lot, University of South Florida, to invite me and to. It's the first time I'm in this campus. Of course, I spent a lot of time in Miami, and I have been exposed to quite some of you. I'm blinded here. I go over here to some of you. I was sailing with Alpine on the Australian offshore Australia on the Marion Plateau Lake of the Ocean Drilling. Phil, we cooperated during our PhDs at the Rosenstiel School, and of course Dave is an old-time ETH colleague. So I was always in touch, but it's the first time I'm here. It's superb, location, infrastructure. I'm really happy to see this and to yes, exactly. But we have the ocean, and that's something we miss in Switzerland. So today, I'd like to talk about tsunamis in lakes, which is a bit. Some people say, what's going on there? So that's not really what one expects as one of the natural hazards in landlocked countries. But in fact, I will explain you that tsunamis already but there were some victims already in Swiss history. So it's a real hazard, and we want to understand a little bit how dangerous it is and how often it occurs and what's behind it. And of course, to prepare for this talk, I thought, Gulf of Mexico, tsunamis, there must be a history. So I Googled a little bit, and I didn't find a lot. I found some reports from the USGS that made some studies, and I found this poster here from a group from NOAA, and it lists all the historic tsunamis that occurred in the Pacific coast, the Caribbean, and the Gulf of Mexico looks awkwardly empty. So there is not real evidence of historic tsunami activity. Correct me if I'm wrong, maybe the poster lies, but I will show you also that the absence of evidence is, of course, no evidence of absence. And recent data has shown a lot of mass movement deposits in the Gulf of Mexico along the Mississippi Canyon Delta. And in fact, that's what we also learn here, that it's the mass movement history that's the key. And you bet that there is a certain tsunami hazard also here along the Gulf Coast. Okay, just the intro. The fact that tsunamis actually do occur in Switzerland has also reached our politicians. So this is a picture of the media room of our federal parliament governmental building. So that's in Bern, in the capital. And they made this new, and they asked the artist to make some wall paintings. And he placed the Matterhorn here next to this famous Japanese icon of tsunami. That's Hokusai, a Japanese artist in the 18th century. Same time as my house, who did that, and somehow they juxtapose here the Swiss symbol to a tsunami wave. We're not really sure whether we inspired them or whether our research inspired them to do so, or the artist. But of course, here it's meant, of course, also in a political term. But what we're going to see is the real Swiss tsunami by looking, for instance, at Lake Lucerne, and they're going to tell you that in fact it's a real hazard. It has occurred, and it will also occur again. Okay, so looking at Lake Lucerne, you see the edge of the Alps. We're looking south. That's the main crest of the Alps. City of Lucerne is down here. And when you think of tsunami, you often think of earthquakes. And there is a certain earthquake hazard in Switzerland as well. It's intraplate these days. So we're not really along one of the major plate boundaries, but we have let's call it a medium seismic hazard. That's from the Swiss Seismologic Service, the earthquake hazard map, the likelihood of a certain ground acceleration. And these are some of the largest events we have. So we have magnitude 6.6, or I focus a lot, of course, on the one close to Lake Lucerne. That's the lake we've just seen. So magnitude 5.9, about 400 years ago in the year 1601. And I focus on this one because we were somehow lucky. So when you work in paleoseismology, you have to be lucky to find good historical documents to calibrate your natural geologic archives that do record earthquakes. And our chronist is Renward Zisat. He was the city clerk of Lucerne, and he wrote an unbelievable book. So it's a thick book about this form, and I could once see the original, so hundreds of pages of history of Lucerne, and he also tells the story of the earthquake of 1601. And in fact, I myself, I cannot read it. It's written in old German, a special type of writing. So we zoom in this view here. And so I can't read the text really, but I can read numbers. They were the same, 1601. So here it says 1,000, and this sentence says that in some parts, after the earthquake, some parts of the lake, the water reached 1,000 Schritt, 1,000 steps, or 3 Büchsenschüsse. This is 3 gunshots far on land. So he reported some areas where the water reached 1,000 step on land, 1,000 step. I mean, if you run away from a tsunami wave, maybe it's 500 meters or 1,000 meters that the water reached the land. In other sections of this document, he writes that he found floating items the day after that were in trees around the lake up to 2 halbards high. How high is a halbard? Maybe 2 meters. So we certainly had a wave of at least 4 meters, maybe 5 meters in some areas of the lake after the earthquake. So we have really incidents that the water was behaving strangely after the earthquake. He also describes the view of the city just taken. It's a wood carving taken 4 years before the earthquake. These are the mills. Indeed, that's the outflowing river, and it has mills in there. And then he was reporting that actually, after the earthquake, every 10 minutes the water was not flowing out but into the lake, and the people could cross the river dry feet. And every 10 minutes the water came again, and this movement lasted for several days. So obviously the lake was in big turmoil. So it was, in addition to the first wave, there was an oscillation that lasted several days of several meters of amplitude. Of course, that was before the Enlightenment. So people thought that this is God's punishment, and that's somehow our duty now as smart natural scientists to look for the real reason for this. This was one example. There's a second example about 80 years later, where in the same lake in another area, this house got totally destroyed. So the wave was up to this place, up to the second floor. All the windows shattered, the boats were destroyed, and they had to rebuild it eventually, that it looks like this again. And there was no earthquake at this time. So there are some tsunami events some big wave events on the lakes which are not related to earthquake shaking. And this leaves us with some questions. And to answer that, to understand these events, I zoom a little bit back. I mean, what's a tsunami wave? That's a classic surf wave in Hawaii. You had 20 meters. That's a total harmless wave. Happens every day, somewhere on the earth we have these waves. It's only harmful for this guy. But if you compare the amplitude with, for instance, the 2004 tsunami in Sri Lanka, which killed tens of thousands of people, that had only 3-meter amplitude. And of course, it's a different physics, which I don't go in detail. You might know all this. So the tsunamis just have a huge wavelength, thousands of kilometers. And so it's a different physics behind it. It's a low amplitude wave, but with huge wavelengths, and that makes the hazard. And I want to point out a little bit that we also can simulate that later on with what happened in Lake Lucerne. We have 3 possible ways that we can actually create a tsunami wave. So we have the classic one, which is what we've heard from Indonesia, from Japan. That's the classic subduction zone tsunami. I quickly show this animation. We have a subducting plate. it's going down. This is all known from, oops, doesn't work. As we learn it at school and in the newspaper, so we subduct, we create tension, the subducting plate, the hanging plate pops up, and we have then the propagation of the tsunami wave. Now, Switzerland is not active at a super active plate boundary, 1,000-kilometer long plate fault. So that's a mechanism which we cannot account for in the Swiss lakes. But I go back to this slide. Oops, wrong place. But we have a second way, and that is that we do subaquatic mass movements. So if we have subaquatic avalanches of sediments, we can displace a lot of water and we can create also a tsunami waves. And I will claim later that the physics is exactly the same. This is why I call them tsunami waves. There's a third option, which you can have a subaerial rock fall into a water body, very violent. This can create gigantic waves. This affects the upper part of the water column. And I personally don't call this tsunami waves, but you may call this tsunami waves. Some people call these impulse waves. I will not talk about this, which is an extra hazard that we do not consider in this talk today. So let's focus on this one, on the subaquatic mass movements. And if you go back to 3 months, when in Indonesia, in Palu, was this horrible earthquake, which was followed by a tsunami wave, then I was on all these chat groups. They say, well, this was a strike-slip earthquake. It was not a subduction zone earthquake. This is a fault that goes through the Indonesian archipelago, but it's not subduction zone, it's really strike-slip. And that should not really make a tsunami wave because you have no vertical movement. So the idea is that pretty much the community agreed that we have probably a lot of mass movement triggered in that strait, which displaced the water, which could have caused that tsunami. And in fact, that's the same idea we have here. So most likely these waves were caused by mass movements, and you're going to look for these mass movements. And do we find witnesses of the mass movement? Because it was only 400 years ago, so we should see it. Now, in order to do this, I use a technology which is widely applied also here at this university. We use a multi-beam bathymetric device, and I'll just show you a little bit our setup. So we have this tool here mounted in front of that vessel, which we borrowed from the ETH Zurich, and basically we chart lakes. Standard technology. In lakes, it has not been used a lot. In the States, there's been Lake Tahoe, which has been surveyed, I think 10, 15 years ago, but that was one of the first ones. So we did it now for 10 years. We started this. And actually, we successfully mapped these lakes with our tool. And that's an example from one of the lakes. But there's one thing that we sometimes regret, and that is the shallow water zone. Here in gray. The depth, we usually go only to a water depth of 5 meters, because then it becomes really tricky and it's a big effort to chart. And we use a second technology to get the shallow water part as well. And I think this is something that also here is done, or that could be done, or it has been also applied here. We have very clear water, so we can use LiDAR technology, the green LiDAR with a longer wavelength, with a longer laser wavelength, to map the lake floor. And this we can do in an airborne style. Much simpler, so it's done in a day, but the processing then takes much longer. So basically, the shallow water zone we chart through the air. And this is just one example of a port in Lake Constance. So you see here the 3D view, and this is the profile view. But these are sailboats floating here in a marina above the lake floor. So you have a very nice return here from the lake floor. Of course, it means you also see the water. You have to do a lot of processing and classification in this system in order to get the topography, which is this one, what you want to use. But then once you have done that, we basically take from the deep water, we take the signal from the lake floor, from the multi-beam bathymetry. In the shallow water, we take the LiDAR, the green LiDAR data, and then with this visualization, basically we see this is multi-beam bathymetry data. That's the grid already. Here the point cloud from the LiDAR, and we merge and we get a seamless bathymetry of that lake body. And it's really nice because like this we fill the shallow water zone, and in addition we also get the coastal zone at the same overflight. So we can also use it to map the coast. So we have then we can start explore. And just if you zoom in, for instance, that's one of these. This is high quality data. So we work usually with a 1 meter grid. In the shallow zone, even with a 0.5 meter grid in the water. And that matches then well the grid here in the shallow water and on land as well. So a very nice tool to basically explore these lakes at a scale which nobody has seen it before. So we always say it's like looking at the lakes as if they had no water. And that's new for the lakes in Switzerland. That has not been done before. And the Federal Agency of Topography, the Swiss Topo, actually made all our data public. So basically you can go on the online server, you can choose on land the LiDAR data, and in the lakes you choose our bathymetry data. It's public, you can zoom in, you see all kind of at resolution you want, so that's all public, that all became public data, mostly paid by tax money, so it should be freely accessible. That's the philosophy behind it, and we see kind of, that's gravel mining, here we see a landslide, and that's a subaquatic spring at 100-meter water depth. So it's basically, it opens up extremely new ways of exploring the lake floor, because nobody has seen it before. Okay, back to the topic, back to Lake Lucerne. So this is the map now of the lake. So we merged the LiDAR data on land with the subaquatic data, and we see a lot of morphologies, and we're going to focus a little bit in here. So because we still look for the mass movements that potentially might have caused this earthquake. And we zoom in this part of the lake. So we are between 40 and 150 meter water depth. And you see already here now quite nice, these topography. So that's the flat basin floor. You see on the slope here smooth surfaces and rugged topography below. You see this sharp edge that's about 8 meter high. And it really looks like a snow avalanche. So we have a sharp scar surface, and then we have here in the basin like the avalanche lobe that somehow run out into the basin. So we have a very nice expression of this mass movement. And I will show you later that in fact these were really triggered by this magnitude 5.9 earthquake in 1601. We do find this also in other lakes. Here Lake Zurich, we have exactly the same sharp edge, transition phase, and run out lobe. And you see here mass movements of different age. So that's a fairly young one, it looks fresh. And that's an old one that is already partly below new sediment that accumulated since it went down. By the way, Lake Zurich, a really expensive area. So is that a hazard? We don't know, maybe not. This is just the soft sediment effect. But of course we see in other places that we also have bedrock slides into the basin. Okay, so we do have these mass movements. So how can we date them? So what we do is that we map the deposits using seismic data. That goes now across the basin in Lake Lucerne. The mass movement came down here. Here you see kind of these avalanche deposits, how they accumulate. Here kind of a wedge like a taper running out by a kilometer into the basin. Thickness is up to 8 or 9 meters. And then you see here kind of a unit that overlays it. And so we have here kind of the mass movement itself. And this is, we claim this kind of the turbidite, the suspended particles that settled after the event passed by. In order to prove this, we can take sediment cores. And it's Lake Lucerne, so we take here 2 meter long sediment cores, and you see that's the current lake floor. And you see that the black color on the top, that's Dave, you're a specialist on the eutrophication signal. So that's 50, 60 years of extreme eutrophication, algal blooms, anoxic bottom water conditions, so that reflect this. It's not a topic today. So we look basically here at about 1 meter, and then we see that we hit here a total homogeneous section. It's in this core, we didn't bottom out, so that's the turbidite, that's down afterwards. And here we see the disturbed sediments, that's the mass movement, that's the deformed sediment that is running out into the basin, into the basin floor. And of course, when we can date this, we could date this and we could assign this to the 1601 event 400 years ago. So that's kind of the methods that we apply, and we have pretty good control on what volume comes down, where does it go to, and what's happening. And as a side remark, we looked now at the most shallow event. This is the 1601 event. If we map similar deposits throughout the stratigraphy of the basin fill, we can establish what we call an event chronology. So in this case, we have 15,000 years of history, the post-glacial period. We have about 6 horizons along which always mass movements do occur. And then we actually go towards a event chronology. We say we had in the last 15,000 years 6 events somehow similar as the 1601 event, and that opens up the doors to paleoseismic reconstruction. So we do earthquake recurrence studies that feed directly into seismic hazard assessments of an area. I'm not going into that today because that would be another alley. But we use these to identify past earthquakes. That's what we do with these mass movements. So the topic today is tsunamis, and this then somehow is the process that responsible for tsunamis. So we have an earthquake or not. We have a slope stability, water slides down. Where it slides away, it drags down the water column, and where it slides into, it pushes up the water column. And that basically, coming back to what I showed before with the classic tsunami propagation, that's the same physics. So the water column actually doesn't care whether you have a popping up plate or whether the water column is pushed up from the bottom by some million cubic meters that run out and that move the water column up. The physics is the same. And this is why this process also does a classic tsunami wave, because at one point you lift the entire water column, at another place you draw down the water column, and then your wave starts traveling with a fairly large wavelength. So the physics is the same, and in fact I will show you that we use the same codes as for oceanic tsunamis.
How does lake depth impact the size of this?
Yeah, but it's twofold. So first of all, you need the gradients to get the instabilities on one side, and then you need, of course, it shouldn't be, I'm not sure how much it affects, whether it does affect the amplitude to, in theory, not too much. It's of course, the topography is a first order input. I get back to this. So we see that topography goes in. As a sensitivity, it's not of prime, so it doesn't really matter too much. It's much more important, I showed this, the speed it comes down, the material properties, and so the cohesiveness of the material, and the volume, of course.
Strike of the lake doesn't make a difference either.
Yeah. I want to give you one example. So we look at one part of Lake Lucerne. This is actually where our historic source reported the inundation. That's today an airport, so it's a delta plane. And the 1,000 steps actually he described here. In fact, this is also along this coast, at least I think 10 people died from the wave. Not from the earthquake, but from the wave. So it is a hazard that can cost lives. So we know that without making here a big drama, but it's just a natural hazard which we want to understand. So let's look at this part of Lake Lucerne. So we do what I just described. So we do a bathymetric map. So here you notice that we did not do the LiDAR survey, so we only have the deep water parts covered. This has to do that in this case we did not have too much interest from the biologists, because usually it's the fishery, the fish people, the biologists, the coastal zones, ecologists who are keen to know this data. In this case it was just us who did this first lake in Switzerland to survey, so we were on our own, and we could not find, at this point also the LiDAR technology was not developed that much. Okay, so here we see the bathymetry, and we see similar features. So we have here these scar surfaces all over. So we see all this mass looks like this part was really sliding down. And this is confirmed with the seismic line that goes through here. If you look at this seismic line, so we see this avalanche deposit here. Again, that's the debris flow itself. And you see this transparent unit. That's the turbidite overlying it. Watch the thickness, 8 meters, up to between 8 and 10 meters. So three times this room height. And the total volume that came down 1601 in this part is 50 million cubic meters. So 50 million cubic meters of mud were triggered by this slope movement. And now if you want to model this, just to show off a little bit here with these things. So we actually do a twofold model. So we have a first, it's all on public domain model code. So we use the MassMove 2D software to somehow model the mud avalanches that goes down that slope. So all subaquatically. So we need various input parameters. We see the shear strength, the density, We have some conceptual models, so we use it as a Bingham fluid, kind of to go down. And this is a first model, and by this model, it kind of executes the downgoing mud avalanche. A second model, which is, we use the GeoClaw software, shallow water equation. Somehow a second model simulates how this mass movements convolves the water column. So we need two models, one for the mud movement and one for the water movement. These are the codes, and let's look at this example. So here, the mud avalanche goes down. So in this case, we have these 50 million cubic meters that actually descend with the height of, the maximum flow height is 35 meters. A gigantic avalanche that go down. At the same time, it triggers this wave. So this is the propagation of the wave, which we call tsunami-wave, because it's the same physics as the oceanic tsunami waves. Here we have a maximum wave height of 10 meters, so maybe we exaggerated a bit on the speed or on some of the properties, but actually we think that on the open lake it reached also 10 meters in 1601. It's really interesting to zoom in on this field, because this is what we want to use as calibration. Were these 1,000 steps, were these about right? So we want to tune our model so that we get about 1,000 steps. And if we zoom in this model, actually it's quite fine. So we see the wave approaching, that's today's airport. And we observe basically the same features as we've seen in all these videos from Indonesia or Japan. So we see the inundation. We also see how the waves comes in different pulses. So actually you have backflow, inflow, backflow again. And after a while, it's all in resonance. So there comes, I think just now comes then a second large wave that comes in that does another push of inundation. So what we see here is about 1,000 steps, so that's about 500 meters. So it matches well that historic description, and I think we are on good track to understand that hazard and to quantitatively kind of being able to simulate it. But of course, this state, we are still somehow a little bit on the back of an envelope, because we have some ideas about rheology and these processes of the sediments, but we want to improve this. So to finalize this example here, that's kind of the inundated model according to current topography, to current settlement. So we know if this would reoccur, we would have this flooding in these zones. And please note that the church of this village is 2 meters higher, a little bit raised, so the church survived. So go to the church when you have a tsunami occur. So that's kind of a simulation today. And of course, this is a classic image which we try to inform. So we don't want to sell it or make panic or so. We just say we want to educate about these tsunamis. I get back to this at the end. In order to verify this, to get a better control, we just started, in fact, a large project. And in the next 10 minutes, I want to show you a little bit the elements of this new project. So what are we doing these days? And it's a project, a Synergia project funded by the Swiss National Science Foundations, which consists of a series of modules. And that's the webpage. It's a 4-year program. We just entered the second year now, but I can show you some elements of this, and the idea is here to understand the hazard, to understand tsunami formation. And in our proposal, and we really believe that, so these are our model oceans. So we want to use this as a model ocean because it's a confined system, and our goal is to apply new codes, new methods or approaches that we can also apply in the marine realm. The advantage here is that you have the whole basin. You can look at it in an entirety. That was the old credo of your co-supervisor Ken Xu in the 1980s. Use the lakes as model oceans. That offers a lot of advantages as well. Of course, only somebody living in a landlocked country says that.
It's a mini ocean.
Yeah, it's a mini ocean. Yeah. Okay, let's look quickly at these models. So the one is called response, and that's really to get the geotechnical control on the lake sediments. I want to point that out a little bit. So we do, in the slope, we do, for instance, geotechnical testing. We enter probes, kind of vein shear tests to determine the shear strength. We do CPT, cone penetrometer, measuring also shear strength and pore fluid pressure in the sediments, because these are big factors that do influence these slopes. And an example, so this is from Lake Zurich, how we do this. So we have this, I showed this before. So basically we probe the hell out of these slopes. So because we want to understand why did this slide, what slid away, and these areas, of course, we want to understand why did this not slide? Why did the same shaking not trigger a slope instability here? And this is a little one that just went, but that did not really go. So was there a reason that we have threshold conditions here? And then, so that's Michael Struppel actually who did these studies. So he comes up with a mechanical stratigraphy here of a 7 or 8 meter thick sedimentary section. We determine shear strength, bulk density, and then we have kind of two ways to calculate the stability condition. So we can do it deterministically using a factor of 50, which means if it's above 1, then we're safe. Below 1, it's unsafe. So that's kind of the deterministic approach. So more sophisticatedly, we can do it in a probabilistic way, which is state of the art, so that we kind of calculate the probability of failure. How probable is this slope to fail? You see here, basically, all values are below 1. So the probability is not very high because this is the static slope assessment. That's without dynamic loading from an extra earthquake. So actually, it stays, so this should stay. What we then can do, or what Michael Struppel did, he can add, in order to the static situation, he can add some ground acceleration. So we simulate earthquakes. So we know that the strongest earthquake we can expect has maybe 10% G as extra ground, peak ground acceleration superimposed on this slope. And then you see that, for instance, the probability of failure then approaches slowly 1. So we have a really high probability of failure when we shake this slope strongly. But it's important to quantify this in a probabilistic fashion. So we get kind of a hold on how much would be released when a slope is shaken. To get even a better answer on this, we now started to do some ocean bottom seismometer testing. So we took marine ocean bottom seismometers. I'm not aware that they have been deployed actually in the lakes. So we actually put them in, and we want to really measure the resonance frequency of these slopes, charged slopes. So we do like a seismic microsonation underwater. And that's, I think, also something new. So we want to do kind of like a hazard map using a seismic microsonation underwater. With all these tools, and that's quite an operation. So here we see part of this in Lake Lucerne again. So we use huge platforms to lower these heavy instruments. They have acoustic release, so it's really a complex project. This we do with the geophysicists at the Swiss Seismologic Survey at the ETH in Zurich. This is, for instance, an array of ocean bottom seismometer which were placed on this slope. So afterwards we go out with our multi-beam and we image them for precise location, because you never know exactly where they land. And then based on this, the geophysicists do a variety of measurements. This is, for instance, the Scholter wave resonance frequency, which is a surface wave. And we try to distinguish the different properties by looking at the resonance frequency. And the bad news here, and that's a new finding, the bad news here is that the resonance frequency is in the domain of the strongest earthquakes, where also the strongest earthquakes have the peaks. So that means that they are very likely to fail because the earthquakes shake exactly in a way that triggers the resonance of these slopes. Bad news. It also means that somehow we cannot take the amplitude or a measured acceleration on the shore on bedrock, and we cannot translate, say that's 1-to-1 also here, because we have to amplify it in the lake. And for this purpose, we were lucky with the period we placed it. We had some nice earthquakes to occur, one nearby in the Rheingraben. But this is also then the one earthquake that occurred in Hawaii last year. I think that was a magnitude 6 or something in Hawaii, or 7 in Hawaii. So actually we could identify this. And this we will use to do the microsonation underwater. Another module of this project is to look at tsunami layers. So we want to look at coastal sedimentology, to look where we find witnesses of these tsunamis. So that's a coastal plain, again on Lake Lucerne. We have various drill probes. We encountered this as more difficult than expected. So first of all, lakes do not have this nice back. Let's say the ocean often has a beach line, has a berm, and behind a depression where sediments can accumulate. Here we figured out that looking at Lucerne, for instance, this would be a good place, but it has completely been altered by human development. So many of our archives are destroyed. Nevertheless, we core these places. Here is an unaltered plane. We can do coastal stratigraphy, and we do find nice candidates for stratigraphic layers that do reflect the tsunami layers. We think so. We haven't dated them yet. That's all new data from Valentin Nick, who does a PhD thesis. But we see layers like this one where we have coastal peat, and suddenly these in the CT scan here, the dense grains that have been washed in. We think it's tsunami layers, but we have to prove by dating and by sedimentology and physical grain size that this is really a tsunami wave and not a flood. That could also be an issue. So that's a challenge that Valentin faces here. Okay, another module is the wave. We call it module wave. We want to understand the wave propagation. We do it twofold. We do it on one side with the colleague at the ETH studios at the VAW, which is a hydraulic laboratory, with analog experiments and also with numeric modeling. And this is a numerical modeling sensitivity analysis, which I just showed that we do this. So we can, for instance, change the volume, the dynamic viscosity, the shear strength, or some numerical parameters, and we just compare the resulting wave. And if we do this for water depth, this was your question, so it's not a large dependence on that. So it was not included in the prime parameter. So we are tuning somehow these numerical models to simulate the waves, but then matching or complementing these numerical models, we work with these, or my colleagues at ETH work with these tank models, so analog hydraulic experiments. This sounds old-fashioned, but actually it's really good because you do the dual approach. You observe this, you measure this, and the way this looks is like this. So we just started. They just started with, for instance, this one. So you have a tank. You let the mass movement down. You observe the wave. You scale, of course, all the parameters. You have to downscale it to laboratory dimensions, but then you have all kind of cameras and laser scanners that measure the wave, that propagates, and relate the wave height and the wave propagation to the size. So that's an approach here. And in the end, we'd like to make a hazard map, coastal hazard map for coastal communities, possibly in a probabilistic fashion. Okay. So, while we did all this, a journalist became hold of that. And she played, I guess we'd like to publish in Nature, and journalists also like to publish their stories in Nature. And she published that story. We had a mandate from one of the states, and I got in big trouble for this article because that was supposed not to go public at that time. But anyway, so the state of Nidwalden on Lake Lucerne gave us 2 years ago this mandate and said, can you tell us, we heard now this story of 1601, is it really something we have to worry about? So they somehow prematurely wanted to know the results of our large project, and then we said, okay, we do the exercise now. It's a bit back of the envelope because it's premature, but I want to take you at the end now, just take you through this exercise, and that was the base for this article, which actually was nothing bad, but the problem with the article was that it ended with that this state, which is a low-tax, high-income resident state, many lakefront properties. This article ended with that the state will change the building codes along the lakeshore, which was totally out of context. And that was a problem then. That was the true problem. So, yeah. That was the real problem, the rich lakefront properties. Okay, so let's go through this last 5 minutes through this exercise. So Lake Lucerne, we've seen that. So we talk of Nidwalden, which is this area here, and the area there. And so what do we do? So now it's different. So before we had the historic example. Now we look at the current state. So we want to know with the bathymetry, so where are the charged slopes? Where are the potential charged slope that could go down? So you see, that's a scar from 1601. So that already went down. Here we had some avalanches. But we do have here some areas which were not released during the last earthquakes. And we look at this one, a nice slope, charged with 15 meters of sediment, just waiting to be shaken, to go down. 15 meters, that's a lot. So we identify where these places is with geophysical data. So we can make these maps, kind of mapping the amount of sediments on the slopes. Then for this we apply our concept of mechanical stratigraphy. So basically with the shear stress and with these failures we can see where the potential failure surface would be. So we have to know where the material start moving off. Then we do these safety evaluations. So in this case I show you the deterministic model. So we say the resisting forces and the downgoing forces, and we see here dependent on the slope angle and the thickness of the sediment where we enter the red domain. And these are all input parameters to get kind of 2D models here for a seismic acceleration of 0. That's the static case. You see that everything here is in blue, which means it's safe, which is what we want because this is static. This is as it is now. Otherwise, they would be released just automatically. And here we put in a pseudostatic acceleration of 0.7. And then we see the first parts that actually start sliding. And based on these stability calculations we come up with here in the case, I think we have about 25 areas which will become unstable during the next earthquake. So that's the first part of this analysis of the current hazard. Then what we do is, so actually Michael Hilbe does that. He's the person who did my colleague who did all the wave calculations and this mapping exercise. Then we do the same as we've seen before. So we trigger all these avalanches subaquatically and we look at the related tsunami waves. And then the state wanted to have the worst case scenario. And worst case scenario means that we take all 25 parts and we release them all at the same time. So let's do this worst case scenario. So that's how it looks then. And then we have all these masses going down, and then of course we can zoom in along the coasts, and then we can do inundation maps. And that's basically what they wanted us to do. And if you look at this in more detail, so we can map the output product of these simulations, or the run-up height or the inundation distance. We can make maps. And now the funny thing is that they wanted us to use exactly what they use for the rain floods. So in Switzerland we use a flood intensity, which is the product of the speed of flow with the height of the inundation. So basically 1 meter per second flow, 1 meter height is 1. If you have 2 meter height, 1 meter per second, you have 2. And so, of course, that's now applied. So that's an output map for the public, almost strong, medium, weak. These are the categories which we wanted to produce. And then we can do that. And that has the same color code as along the rivers, where they have the same kind of the flood hazard to quantify. And so we did this. And of course, then for us, it was interesting to go back to the same place as we were before, the 1,000 Steps area in 1601. Remember that this was now the map for there. Now, of course, it's interesting to compare what we've seen from 1601. This is this map, our model from 1601, and that's the current state, the current maximum worst case inundation. And if you compare this, we see that, whoa, actually, they were happy to see this. So the current state actually has obviously less hazard than it was 1601, although the earthquake in the worst case, we took really a bad earthquake. So what's happened, of course, that 400 years ago, a lot of the material was mobilized, and those 400 years are not enough to recharge substantially the slopes. This is somehow good news. Nevertheless, there is an inundation hazard, so we delivered this product, the map with the inundation map. And the question now is, so what do we do with it? Is there something to do? Is there a mitigation you have to start? And I want to end this a little bit philosophically here. I mean, here we see the tsunami hazard. That's Fukushima. That's the tsunami wall in front of the nuclear power plant, which was not high enough. Of course, Japan, we have a big earthquakes in average every 100 years. The geologists could have told, it was published, that the waves can be higher than this because there were tsunami layers identified in the area. So what does it mean? So do we now build a wall around Lake Lucerne? Talking of the lakefront property. of course, that's not the solution. So we're not going to put a wall. And it's also, we have to consider now let's go back to reality. So how often do these tsunamis occur? And the big earthquakes that really trigger tsunami, we talk of, let's say, a recurrence rate of 1,000 years, maybe 1,500 or 2,000 years. We have the spontaneous ones, which are usually the delta collapses. They can occur more frequently. But in average, let's say a 1,000-year recurrence rate for these big events. Insurances count only like a 500-year recurrence rate. So it falls through the building insurances mesh for private homes, for instance. So they do not consider this significant. On the other hand, 1,000-year event, 4-meter height, same height as Sri Lanka or Indonesia, so the threat is there. I didn't say this, but the wavelength here are in the range of 1 or 2 kilometers. It's not 100 kilometers like in the ocean, but this is a hazard. And I was once asked whether I would buy a house along the lakeshore, whether I would take that risk. Then I said, well, at the lakeshore front prices, I certainly cannot buy a house in Switzerland on the lake. But with 1,000 or 2,000-year recurrence rate, I wouldn't mind probably for a private home. It's
Cultivate
not.
the fear.
Yeah, exactly. But of course, would you be willing to build a nuclear power plant here in the flooding area? No, because for a nuclear power plant or a hospital, you would not take the 1,000-year hazard as relevant, but the 10,000 or 20,000-year hazard. For instance, our nuclear power plants, they have to be calculated for a 10,000-year hazard. So they definitely fall in that mesh, and we don't want to have our nuclear power plants flooded with the cooling intake by a tsunami wave. We know what can happen. So kind of that's the game we plan. And my main message to the Swiss communities is always, and maybe that's the same also for the Gulf of Mexico community, is that I mean, it's information, it's education. I mean, if I play with children on this beach and I feel the earthquake and I see the water running out into the lake, I'm not running back with the children picking up fishes. So I move to higher ground. So it's this knowledge that we have to foster. It's a rare event, but it can occur anytime. And if it occurs tomorrow, and we have not done this, what I just did in the last 45 minutes, I will be asked, so why didn't you warn us? You knew that this can happen. So that kind of the game we play as educated natural scientists, and I mean, this is an example from the Caribbean. So they have education there, escape route, so they know where to run when the siren goes off. The real-time warning in our case is a bit tricky. We only have, let's say, 2 minutes. So we only have 2 minutes to warn the people. That's just a little bit tight. On the other hand, if we think of what happened in Indonesia, in Palu, many people died because of the tsunami. Same height. So they had first the earthquake. The warning system did not function. Now you may say, in the case of Palu, the earthquake, so the same people who died, they felt a magnitude 7.5 earthquake 20 minutes before. I think that's super tragic. So they had a 7.5 earthquake that killed many people, that had a lot of earth flows, liquefaction effects on land, but they did not evacuate the ocean shore because the tsunami alarm did not go off. In this case, they need no alarm. They have a magnitude 7.5 earthquake. In the case of the volcano that erupted, that had a flank collapse 3 weeks ago, it's a bit different because that falls through the mesh because it's not caused by an earthquake. So there you need real-time buoy station, which exist, but you cannot place them so closely that you can observe all the bays, all the coasts along the lakeshore. They also had about, I think, 40 minutes or so for the wave to arrive, but because it did not do an earthquake, that was really bad luck, to say. But in any case, I think education, information is needed, and this is somehow the motivation we have. That's what we want to give across. At the same time, doing this, we want to research the tsunami generations and propagation, and I think some aspects that we characterize the slopes here can really be applied to sediment-charged slopes in the marine oceans as well. And as we know now from Palu, so this is a process that is also very dangerous and that is somehow one-to-one translatable into the into the aquatic environment on these aquatic slopes. Okay, thank you very much. It was a pleasure. I hope a bit the motivation and results of this exercise we do, and I'm ready for questions, please.
Is there any reaction from the insurance industry on the lakefront problem?
Not yet, no. So they have not. They are aware of it. Yeah.
Insurance companies.
Yeah. Yeah. But it's really an issue. So for all the buildings, for all the regular buildings, if you have, if you say the 500-year hazard is not significant, then that's the scheme they apply. So for insurance, basically, and this one doesn't matter. The motivation of the state was not to build a wall. The motivation of the state to get this inundation map was they wanted to know where, in case it happens, where are the hotspots that we have to do rapid response help.
But 500-year hazard doesn't mean every 500. Nobody
Yes.
can predict.
It's a probabilistic assessment.
Maybe next year, 10
Yeah.
years. Or
Yeah.
So they don't react at all?
Yeah. No, because from well, maybe they will, but because from a financial, statistical approach, it's not important. But from a safety, from a safety thing, it is important. So so I think if you just think of, if you're a hardcore financial insurance advisor, I think you say this, should we put money aside for that?
Okay.
Probably not. Yeah. But it's a good point. Huh? So,
That was wonderful. I got a zillion questions, but I'll only ask one or two. We can talk in the next day or two if you like. A colleague of mine, Hank Mullins at Syracuse University, and I shot a lot of seismic in glacial lakes and
Finger Lakes.
Finger Lakes, yeah, and also out in British Columbia.
Yeah.
So I'm curious about, for instance, sedimentation rate. Sedimentation rate doesn't seem to be a variable; it's a constant, and it must be low in these lakes.
Yeah.
So if you had a high variability of sedimentation
Yeah.
rate, that would obviously complicate
Yeah,
issues.
absolutely true.
And also, in the Finger Lakes in particular, we would see in our seismic data acoustically chaotic lenses like you see, but we attributed those to in-wash events.
Yeah.
So we'd have major rainfall events, and rivers would flow into the lake and produce these coarse-grained turbidites, debris flows actually, that would extend out into the lake. There doesn't seem to be much of a paleofluvial or fluvial input into these lakes.
We can distinguish those. Huh? So we have the historic things, so we core them, and by looking at the geometries, we can distinguish them. So basically, these are always these wedge-shaped, tapered things, and then we see the scar surfaces. But the other ones we have too. That's correct, the floods. But your first point is interesting. So the sedimentation rate does affect the recharge phenomena. And it's a complicated thing. If we use the mass movements for paleoseismic indications, so we say we have one earthquake that triggers the slope, 200 years later comes the next, nothing happens, so we miss in our records the earthquake. And each lake has a susceptibility to record earthquakes through mass movements, and that's a function of the sedimentation rate. So basically, that hampers, actually, we are worried about this, so our paleoseismic record reconstructions are incomplete because of that. So we want to have lakes with high sedimentation rate. But then, of course, we get also the delta areas where you get spontaneous aseismic mass movements, and that's also something you don't want to have as paleoseismic indicator. So it's an unsolved issue. But for the current hazards, we don't care, because we can actually map how thick the sediments are on the slope.
Sure.
Yeah.
What about liquefaction? I mean, Lucerne is sitting on a paleo lake floor,
Yeah.
right?
Yeah,
Wouldn't the
partly.
shaking
Yeah.
make the effective stress go to zero with buildings?
Yeah, yeah. We have these, so that all feeds back into the pore water effect on the dynamic loading and on the grain size structure. So what we understand well are the lateral slides. They are all fine-grained and nicely layered, and they have very little connection to some groundwater inflow or so. And then this we can simulate also in the lab. Lucerne sits partly on an outwash deposit, but we have deltas which have similar lithologies, where we have kind of coarse-grained sand layers that feed well into a fluvial system that gets charged by, for instance, if you have a flood event, you increase the pore fluid pressure also in the delta. And through this, actually, you have an additional mechanism, and the delta we cannot model these days, because first of all, we cannot image them seismically because you're not getting acoustically into the delta, and we don't know what's happened to the pore fluid pressure. So, and it's coarse grained, so it's very prone to liquefaction. And this is why we have to exclude it, although we know the historic events when the delta collapse, with or without earthquake. And that's a hazard where we admit, we say, we're not good at, we try, we can maybe improve, but it gets, the uncertainties become larger in these domains. So what I showed today was kind of the majority of the slides. These are the lateral fine-grained slopes, which are not so prone for pore water.
The stratigraphy is basically structureless.
Yeah.
Delta would be
Yeah.
very heterogeneous.
Had lenses and yeah, and because we don't get the seismic image, we just can do sketches. Yeah.
Cool.
But yeah, you got a weak point there. Yeah. Phil.
So Flavio, with that snow avalanches, there's a whole proactive program to trigger these avalanches and reduce the hazard.
Yeah.
So have you guys thought about that?
Of course, it's our dream to blow up one of these slopes. No, seriously, so actually we were thinking of implementing that in the Synergia project. We take a slope, we put sensors, pore water pressure sensors, accelerometers, seismometers on it. We monitor all the water column. We do everything, and then we trigger that thing. But the issues we will not get. I mean, I'm not sure I would push that. I mean, we would not get the permit for that. That's clear. But it would be extremely useful. So we could gain so much knowledge doing that. So the idea then is that we go to a remote lake, that we do it in the Alps, but then these are small lakes which have very small slopes, and the big proglacial lakes are all in the plains, and they are all settled. So we do have actually quite a nice lake that in winter is lowered, and that even in addition has a dam, Klöntal, maybe you know, the Glarus Alps, and that would be actually a good candidate. So we have an extra safety of 20-meter exposed dam, which in winter is popping out. And we have some slopes in there, so maybe we could do it there. But if there's any settlement structure, infrastructure on the lakeshore as usual, I probably would not dare to pull the trigger and to. Yeah.
About 30 years ago, there was a really bad movie made called The Wave, and.
Yeah.
It would be great to see again with a bunch of beer and this community. And it's about a tsunami generated in a fjord in Scandinavia.
Yeah, I know.
And,
Yeah.
and it's evidently based on a real event in which a few dozen people were killed.
Yeah.
Is there a terrestrial equivalent of your program where they're mapping the
Yes.
adjacent?
Yes. This is also something I didn't touch, but it's also something that worries us. And actually, it's only 10 years old or so. Can that be? Or maybe it's a new version of it. But the new version of this Norwegian,
old one, which
it's
is
over.
really,
But there's a new version, and the new version had.
we would say it's camp.
Yeah.
in a-
But there is a really good new version because they had the input of all the Norwegian hazard specialists.
Oh, really?
Yeah, it's a little bit like for the. Like what was it? The Day After Tomorrow, Wally Broker was one of the advisor of the movie makers. So the processes are right, but some details, of course. No, but this subaerial mass is impacting. I mean, that's a total different story. And I mean, there was the Alaskan case of that fjord, which was 550 meter high, Lituania Bay. We had in the Alps the Vaillant case, where a whole mountain slid into a newly raised hydropower lake. That was bad engineering, costed, I think, 2,000 lives in the 60s. So this is a big thing. So we have currently, a big concern is the retreating glaciers. They leave a lot of overdeepened basins behind, which are filled with lakes, which have a big touristic potential, with a beautiful scenery in the Alps. but you have ice mass hovering above it.